Okay, hello everyone, in a new video. So we have reached part 4 of chapter 4, which is the chapter of resistors and the second unit of electricity. Now we have reached section number 17, which is given by short circuiting. And let me state here what is meant by short circuiting. Short circuiting a component means that connecting a wire in parallel across its terminals. Then for this reason, let me consider the following electric circuit consisting of a battery and two electric components. Let's consider that these electric components are resistors. So this is R1, connected to in series with the resistor R2, connected back to the negative pole of the battery. So now suppose that you are interested in short circuiting the resistor R1. So by short circuiting a component means that connecting a wire, connecting a wire in parallel across its terminals. So now we are interested in short circuiting R1. So let's short circuit R1. So what does it mean to short circuit R1? Is that short circuiting R1 means that we connect to R1 in parallel a connecting wire. So by this we have short circuited R1. Now in this case, so the voltage across R1 is 0 because it is short circuited. Now why the voltage across the electric component R1 is 0? Notice that R1 is in parallel with the connecting wire, so according to law of uniqueness of voltages, they have the same voltage, but the voltage across the connecting wire is 0, which means that the voltage across R1 is 0. So whenever we short circuit an electric component, and by short circuiting it means that we connect in parallel a connecting wire, then its voltage becomes 0. So this is it for short circuiting an electric component. Now let's move to the other section, which is given by the rheostat. So section number 18, the rheostat. Now let me give the symbol of the rheostat. So what is a rheostat? The rheostat is a resistor of adjustable resistance. So suppose that this rheostat has a resistance R, then the value of R can be adjusted. Say for example, it can be given by 10 ohms, 20 ohms, 30 ohms. So we can adjust the value of the resistance as we wish. Now, idea number 3, it has 3 terminals. Unlike other components, the rheostat has 3 terminals, whereas other components that we have seen, they only consist of 2 terminals, and the 3 terminals are given by A, B, and C. Notice that C, the terminal C, is related to this arrow. This terminal is called the cursor. So C is called the cursor. Now idea number 4, this cursor C, or this arrow, can move from A to this point to B. Then let me say the cursor C can be moved from A to B. As the cursor moves, the resistance of the rheostat changes. So as we have said previously that the rheostat is a resistance of resistance R such that the value of the resistance is adjustable. We can adjust it from 10 to 20 to 30 as we wish. Then how do we adjust the value of its resistance? Simply by moving the cursor C from A to B. Now on number 5, so what's the role of this rheostat? The role of the rheostat is to change the voltage in the circuit So because this electric component can be considered as an ohmic conductor, then we can apply Ohm's law to it, which is given by U is equal to R multiplied by I. Now after constructing the triangle of this formula, we can notice that R is given by, or let me say, okay, U is equal to R multiplied by I. Now this electric component is a rheostat, which means that its resistance can be adjusted. So as we change the value of R, we expect that the value of U will change. So for this reason, the role of the rheostat is to change the voltage in the circuit, and this is known as potentiometer. Okay, so this is it for the rheostat. Now let me move to the other section, which is converting units. Then section number 19, converting units. Then till this moment we have introduced three physical quantities that are given by the voltage, the current, and the resistance. In chapter 3 we have discussed the conversion of voltages and amperes. Now in this case we need to discuss the resistance. So let me say here that the SI unit, which is ohms, the unit of the resistance, which is ohms. Then let me say the SI unit of resistance is ohms, and its symbol is omega. Now we are interested in converting from mega ohms. So we have seen this line before. We are interested in converting from mega ohms into ohms, as well as kilo ohms into ohms. Now this line is empty. Let's label it by the quantity, which is ohms. So this is ohms. Now in order to convert from mega ohm to ohm, we are moving from left to right, so we multiply by 3, 4, 5, 6 by 10 to the power 6. And if we move from omega or ohms to mega ohms, then this is given by divided by 10 to the power 6, or simply this can be written as times 10 to the power minus 6, okay? So let's say divided by 10 to the power 6. Now in order to convert from kilo ohms to ohms, from kilo ohms to ohms we are moving to the right, then we multiply by 1, 2, 3 by 1000. And in order to move from ohms to kilo ohms, we divide by 1000. Okay. And now let's solve this exercise as a direct application on converting units. Then section number 20, exercise number 11. Convert the following units to the SI. Then R1, which is equal to 6 kilo ohms. Knowing that kilo ohms is not the SI unit of ohms, in order to convert from kilo ohms into ohms, we simply multiply by 1000. Then this is given by 6 multiplied by 1000, which is equal to 6000 ohms. Similarly, R2, which is given by 3 kilo ohms. In order to convert from kilo ohms to ohms, we multiply by 1000. So this is given by 3000. Now R3 is equal to 5 mega ohms. Now in order to convert from mega ohms into ohms, we simply multiply by 10 to the power 6. So 5 times 10 to the power 6, which is equal to, okay, directly ohms. Now R4, which is equal to 12.5 kilo ohms. So in order to convert from kilo ohms to ohms, we multiply by 1000, then this is given by 12,500 ohms. Now R5, which is equal to 16 kilo ohms, then this is equal to 16 times 1000, which is equal to 16,000 ohms. Now R6, which is equal to 17 mega ohm, then 17 times 10 to the power 6 ohms. And finally R7, which is equal to 0.1 mega ohm, then we multiply by 10 to the power 6. So this is given by 1 times 10 to the power 5 ohms. Then this is it for exercise number 11. Now exercise number 12, this exercise is very important. They are telling me an electric circuit is connected up as shown in the above figure. So they mentioned the figure, now we can use it. The battery supplies a constant voltage UPN, which is 12 volts. Then the trick in solving such type of exercises is to label the applied voltage and the traverse current on the electric circuit itself. So this is 12 volts. The two resistors R1 and R2 have resistances 10 ohms and 15 ohms. Let me write here that R1 is equal to 10 ohms and R2 is equal to 15 ohms respectively. Lamp L acts as a resistor of resistance RL is equal to 10 ohms. This is important that here the lamp acts as a resistor, so we can apply Ohm's law to the lamp and bears the following inscription for volt. Then let me write here that the lamp L have the following indication, which is given by 4.5 volts and a resistance RL is equal to 10 ohms. And let me erase this. Now in number 1, they are asking me the voltage across R2 and L is the same, justify. So notice that the lamp L and the resistor R2, they are in parallel. And whenever two electric components are in parallel, they have the same applied voltage, and this is given by the law of uniqueness of voltages. Then let's say as a title here that L and R2 are in parallel. So this is statement, usually they give it half a mark. So always we need to mention the grouping. Then let's mention the law according to law of uniqueness of voltages. They have the same voltage, which means that the voltage across the lamp, which is given by, say for example, UL, is equal to the voltage across the resistor, which is UR2. Okay, so they are equal. Now this voltage is given by UCB. Now in number 2, show that the equivalent resistance of R2 and L is R prime is equal to 6 ohms. So as we have mentioned that these two electric components are in parallel, then let's say L and R2 are in parallel. And we are interested in determining the equivalent resistance R prime that replaces R2 and L, which is denoted by R prime. And because they are in parallel, the equivalent resistor is given by 1 over R prime, which is equal to 1 over the resistance of the lamp, which is given by RL, plus 1 over R2. So always we need to mention the grouping. So this is they give it half a mark, and 1 over 4 for writing the formula correctly. Now the value of R1 is RL is given by 10, so 1 over 10, and the value of R2 is given by 15. Now here we need to be careful because we are adding two fractions, so we need to take into consideration the common denominator and the simplest form of the fraction, or we plug it on the calculator, then the value is given by 1 over 6. But notice that this value represents the value of 1 over R prime, in this case R prime. So now if we cross multiply, then the value of R prime is equal to 6. Since everything previously is expressed in the SI, so the value of R prime will be expressed in the SI, which is ohms. And now notice that we have determined an equivalent resistance. And whenever we determine an equivalent resistance, we need to represent this equivalent resistance in the electric circuit. And here notice that the lamp L, which is given by 4.5 volts, I didn't label this voltage on the electric circuit itself because yet we don't know if the lamp is functioning normally or no. So let me here represent this equivalent resistance in the new electric circuit. So this is R1, this is the point C, this is R prime. So here we have that R prime is equal to 6 ohms. And we have R1. This is the electric current I traversing the circuit. And this is the point P, this is the point N, this is 12 volts. Then this is it for number 2. Let me say that this is the point A, C, and B. Now in number 3 they are telling me deduce, and deduce by itself it means that we need to use the previous part, the equivalent resistance RE between A and B of the circuit. Now here in the following parts we always have two electric circuits, so we can refer to either of the two. Because they are telling me deduce, we need to refer to part 2, and in part 2 we have constructed this electric circuit. We need to determine the equivalent resistance RE between A and B. So it's easier to consider this electric circuit because notice that R1 and R prime are in parallel. Sorry, are in series. So why the resistors R1 and R prime are in series? Because simply they have one terminal common, which is the point C. Then in this case, the equivalent resistance is denoted by Re, which is equal to R1 plus R prime. So this statement, usually they give it half a mark and 1/4 for this. Then the value of R1 is given by 10 and the value of R prime is given by 6. And this is given by 16. And because R1 and R prime are expressed in ohms, so the value of Re is expressed in ohms. So Re is equal to 16 ohms. And because here we have determined an equivalent resistance equivalent to R1 and R prime across the terminals A and B, then we need to represent this equivalent resistance. So here we have the battery. This is simply Re of value Re is equal to 16 ohms. Now this is the point P, this is the point A, eventually the point C will disappear, and this is the point N. Okay, so this is the value of the electric current I, and this is 12 volts. Now in number 4, by applying Ohm's law, calculate the main current I in the electric circuit. So here in the following questions, we have 3 electric circuits. We can refer to either of these 3 in order to answer the following questions. They are telling me by applying Ohm's law. So let's say apply Ohm's law. Then we need to determine calculate the main current I in the electric circuit. Ohm's law is given by U is equal to R multiplied by I, which means that I is equal to U divided by R if we construct a triangle. In order to determine the value of I, we need to know the voltage and the resistance. We know all the resistances, but here we should consider the third electric circuit that we have constructed here, because we know now if Re is given by 16 ohms, and we know that its voltage will be 12 volts because Re is only connected to the battery. So in this case, we know the voltage and we know its resistance, which is given by 16. Then we can calculate the electric current I, which is the same for these 3 electric circuits. Here we cannot calculate the electric current I because we don't know the voltage UAC nor the voltage UCB. Similarly here, we cannot calculate the value of I using Ohm's law because we don't know the voltage UAC and the voltage UCB. So apply Ohm's law to Re. Then in this case, the general form is given by U is equal to R multiplied by I. Now we are interested in determining the value of I, so constructing the triangle of this formula. Then here, because we have multiplied, then U will be at the top, R and I at the bottom. Then we are interested in determining the value of I. So putting our hand over I, then I is given by U divided by R. The value of U is given by UAB. And the value of R is given by Re. Now it's clear that UAB is equal to UPN, and this can be proven by several ways, either by the law of addition of voltages, or we can say the law of uniqueness of voltages. Okay, so here the value of UAB, which is equal to UPN, which is equal to 12, divided by the value of Re, which is given by 16. Plugging this fraction on the calculator, then the value of I is given by 0.75. Since both U and R are expressed in the SI, which is volts and ohms respectively, then the value of I will be in the SI, which is amperes. Then I is equal to 0.75 amperes. And the trick in solving such type of exercises is to label the applied voltage and the traverse current on all electric circuits. Then the value of I is given by 0.75 amperes. The value of I is given by 0.75 amperes. And here the value of I is equal to 0.75 amperes. Now in number 5, they are telling me determine UCB, and here we need to refer to 3 different electric circuits. Notice that we cannot use the third electric circuit because simply the point C doesn't appear here. So we are left either with the first or the second. Now UCB, the voltage UCB can be determined by two different laws. By the law of addition of voltages, which is UPN is equal to UAC plus UCB, say for example, because these are connecting wires, but eventually we don't know the voltage UAC. However, we know the value of the electric current I traversing the circuit, which is I is equal to 0.75 amperes. Then we can apply Ohm's law to R prime, because we know the value of the current and we know R prime. Then using Ohm's law we can determine UCB. Okay, we cannot use the first electric circuit, because in order to determine UCB, so this is the electric current I. At the point C, it will split into two currents, which is given, say, by for example, I2 and I3. We don't know the value of I2 and I3, so we cannot apply Ohm's law to UCB across R2 or L. But in this case, we can apply Ohm's law to R prime, because we know it's being traversed by an electric current, I. Then apply Ohm's law to R prime. Then U is equal to Ri. Notice that we are interested in determining the value of U, so no need to construct a triangle, which is given by UCB of resistance R prime traversed by the current I, which is equal to 16. Sorry, the value of R prime is 6, multiplied by the value of I, which is 0.75. Now plugging this on the calculator, then it's given by 4.5. Since all of these are expressed in the SI, so the value of UCB will be expressed in the SI, which is volts. Then UCB is equal to 4.5 volts. And as I have said, the trick in solving such type of exercises is to label the applied voltage on the electric circuits, on all electric circuits. So this is 4.5 volts and this is 4.5 volts. We cannot label this applied voltage here because the point C doesn't appear. Now, for example, in this case, we can determine the voltage UAC using the law of addition of voltages, okay? Now, in part 6, they are telling me the lamp L functions normally. Explain. So notice that the lamp L carries the following inscription, which is the rated voltage, and it has an applied voltage which is equal to 4.5. Then let's say since the applied voltage is equal to the rated voltage of the lamp L, which means 4.5 volts is equal to 4.5 volts, then the lamp L functions normally. Now in number 7, we replace R1 by a connecting wire of negligible resistance. So now R1 is replaced by a connecting wire, and because of this, now we can ignore all of these electric circuits, because the analysis on these electric circuits are based on the presence of the resistor R1. And for the same reason, the applied voltage 4.5 will change, the current will change, and the only thing that will remain the same is the voltage of the battery. Let me represent the new electric circuit, replacing R1 by a connecting wire. So this is the battery. This is the point C. This is the point B. This is R2. This is the lamp L. This is the point A. This is 12 volt. Okay. Now in 7.1, they are telling me give the value of your AC. Now across A and C we have a connecting wire, so let's say the voltage across a connecting wire is 0. So in this case, UAC is equal to 0. Now, because they asked me about the voltage across a branch, we expect that now they will ask me about the law of addition of voltages. Indeed, in 7.2, they are telling me determine UCB. UCB can be determined using the law of addition of voltages. So in 7.2, apply law of addition of voltages. So always on the left we write the voltage of the battery, which is given by UPN. On the other side, we'll go from P to N across different electric components, making sure that UCB must appear in the equation. Then from P to A plus A to C plus C to B and B back to N, we are interested in determining UCB. So UPN is 12, UPA is 0, and the reason is given by connecting wire. We didn't discuss this previously. Now UAC is 0, justified previously. We are interested in determining UCB, so we keep it as a variable. What about UBN? UBN is 0, and the reason is given by connecting wire. So in this case, UCB is equal to 12 volts, because everything is expressed in that side. So this is 12 volts. Okay. Now in 7.3, they are telling me show that the lamp may burn out. So notice that after we have removed the resistor, now the voltage UCB increases across R2, which is the same across L, and it's given by 12 volts, whereas the rated voltage of the lamp is given by 4.5. So let me say since the applied voltage is greater than the rated voltage of the lamp, which means that 12 volts is greater than 4.5 volts, then the lamp we know that in this case the lamp L may function strongly or burns out, but since they mentioned that the lamp may burn out, so let's say then the lamp L may burn out. Then this is it for exercise number 12. Let's move to the final exercise for this video, which is exercise number 13. Consider the following electric devices: a lamp L acting as a resistor, ohmic conductor, and bearing the following inscriptions: 9 volt, 1.5 amperes. So we have a lamp L carrying the following indications: 9 volts and 1.5 amperes. And ohmic conductor means that we can apply Ohm's law to this lamp. A generator G maintaining across its terminals a DC voltage of constant value UG is equal to 21 volts. Now in number 1, if L is connected directly to the terminals of G, it may burn out, justified. So notice that the lamp L has a rated voltage which is given by 9 volts, and the applied voltage of the battery is given by 21 volts. So since the applied voltage is greater than the rated voltage of the lamp L, and this is because 21 volts is greater than 9 volts. So in this case we know that the lamp L may function strongly or burns out, but here they are specifying that it will burn out. So let's say then the lamp L may burn out. Now in number 2 they are telling me calculate the resistance RL of the lamp L. So notice that till this moment we don't have any electric circuit. However, the resistance RL of the lamp can be calculated without considering an electric circuit because the lamp L is considered as an ohmic conductor and we know the rated voltage and the rated current. So apply Ohm's law to L. How come that we are applying Ohm's law to a lamp? Because this lamp acts as an ohmic conductor. Then U is equal to R multiplied by I. Notice that we are interested in determining the value of R. So constructing the triangle of this formula, here because we have multiplied, then U will be at the top, R and I at the bottom, putting our hand over R. Then R is given by U divided by I. So notice that we are not allowed to use the indications of the lamp unless it's functioning normally, or if we are calculating the resistance, which is denoted by RL. In this case we can use the indications because we are calculating resistance, which is given by 9 divided by 1.5. Plugging this fraction on the calculator, then the resistance of the lamp is given by 6. Since everything is expressed in the SI, so the value of RL will be in the SI, which is ohms. So the resistance of the lamp is given by 6 ohms. Now in number 3, in order to let L functions normally, it is connected with an ohmic conductor, so this is important. So the lamp L in this case is functioning normally. Then we can use the rated voltage. It is connected with an ohmic conductor R of resistance R in series with the G. So now the electric circuit consists of the generator, the resistor, and the lamp. Now in 3.1, so this electric circuit, they are telling me in order to let L functions normally, it's connected with an ohmic conductor R of resistance R in series with the G. So we have the lamp, the resistor, and the generator. In 3.1, draw the diagram of the circuit. So this is the battery, this is the resistor, and this is the lamp. Now here, independent whether we place the lamp at the beginning or the resistor, it's the same. We can also place the resistor here, the lamp here, because all of them in series. The order is not important. Now here we have that this is 21 volts. So always the trick in solving such type of exercise is to write the applied voltage, and because the lamp is functioning normally, this is 9 volt as well, that the current traversing this circuit is, so the 9 volts is for the battery, for the lamp L, and the traverse current is given by 1.5 amperes. Now in 3.2 they are asking me what is the electric current I in the circuit. So notice that because the lamp L is functioning normally, then the value of the traverse current is equal to the rated current. Which means that the value of the current I is equal to 1.5 amperes. Now in 3.3 they are telling me show that the voltage across the terminals of R is UR is equal to 15 volts. So we know the voltage of the battery and we know the voltage of the lamp. So we can determine the voltage across the resistor R. So notice that here the voltage is being labeled by the letter R. So this is the resistor R, this is UG. So here we can say apply law of addition of voltages. So always on the left we write the voltage of the battery, which is given by, in this case, UG. Here they are using the name of the electric components and not the terminals. So let's say UG is equal to the voltage of the resistor, which is UR, plus the voltage of the lamp UL, knowing that we are interested in determining UR. So why we are using the name of the electric components and not the terminals? Because in the exercise everything is being mentioned as the name of the electric components. So UG, UR, and because here we have RL, so it's given by UL. Now the value of UG is given by 21. UR is kept as an unknown plus the value of UL, which is 9 because it's functioning normally. Then what's the type of this equation? This is a linear equation and one unknown. The unknown is UR. Then how do we solve it? We put UR on one side and all the other numbers on the other side. So it's given by 21 minus 9, which is equal to 15. Since everything is expressed in the SI, which is volts, so the value of UR will be 15 volts. Then this is given by 15 volts traversed by an electric current 1.5 amperes. Now in 3.4 they are telling me to deduce R, and by deduce it means that we need to use the previous part. In the previous part we have determined the applied voltage across the resistor, and we already know the value of the traverse current. Then the value of R can be deduced by applying Ohm's law to R. So apply Ohm's law to R, and this law is given by U is equal to R multiplied by I. We are interested in determining the value of R, so constructing the triangle of this formula, because we have multiply, then U will be at the top, R and I at the bottom. The value of R is given by U divided by I, the voltage of the resistor, which is UR, traversed by the current I. So UR is equal to 15 divided by 1.5. Plugging this fraction on the calculator, then the value of R is given by 10. Since U and I are expressed in that side, so the value of R will be in that side, which is ohms. Then R is equal to 10 ohms. So what does this mean? Notice that in the beginning of this exercise, we wish to let this lamp function while connected to a battery of 21 volts. But as we can notice that the lamp may burn out, so the convenient way to solve this problem is not by replacing the lamp or the battery, because they are commercially expensive. So it's to connect a resistor in series with a lamp. But the problem is that what's the value of this resistance? Using circuit analysis we can determine that the value of R is given by 10 ohms. So this is it for me in this exercise and this video. So then in part 5 we'll complete solving exercises on this chapter.